Okay, so the way this is going to work, today is another day of what we call enrichment, sort of going a little deeper into how these molecular orbitals are created. You could create these by hand, but after you get to larger molecules, you end up just doing it by computer. But this is what the computer is doing. So how does this apply to what I'm requiring you to know and internalize? This is for your understanding of how these images of atomic orbitals are combined into molecular orbitals. And once again, it's an illustration of what usefulness we have in the character tables. Okay, but we're going to back out of the depth and go back more shallow again on Friday and Monday, where we actually do a couple of MO diagrams. And so there's always this sort of undercurrent in a student's mind of am I going to be required to remember this, right? And so today you're not going to be required to repeat or reproduce a lot of this, but you should know it, like as to how it works, okay? The stuff on Friday and Monday you should be able to reproduce, okay? So once again, just relax. Take a note or two if you want to, but for the most part, enjoy today learning how the computer is putting together these molecular orbitals and how you might do it with smaller versions of the atomic orbitals. And I'll draw some things that you should be able to do on your MO diagrams, okay? So this is the symmetry, this is the projection operator. And this is how we make the symmetry adapted linear combinations of atomic orbitals that we call molecular orbitals. So remember what that word molecular means. It means an orbital that goes over the whole molecule. And so we're leaving local bond theory completely behind. Local bond theory says for every bond in the molecule, there's 2 electrons directly between those 2 atoms. Think about the Lewis dot structure. Okay, and we count every one of those bonds as 2 electrons, as if a CH bond has 2 electrons between the carbon and the hydrogen. That is not supported by XPS or UV photoelectron spectroscopy. What is supported is a molecular orbital, that those 2 electrons are smeared across the whole molecule, and they may contribute to multiple bonds at once and make them stronger or weaker. And this is how those are made using the projection operator. It's a mathematical treatment of the atomic orbitals, and we'll go through the math today at a medium level. Like we can just sort of wave a magic wand and create the molecular orbital. We can do kind of a flyover at about 30,000 feet and say, here's the road, here's the city, here's the river, here's the canyon, and that's kind of what we're going to do today. And then you could actually get down into the math and program Gaussian to do it. We're not going to do that. I don't even know how to do that. Okay, I still know sort of the 30,000 foot view of the projection operator. And now this is also how we get those arrow diagrams. So with the vibrational mode, we would draw the arrows on the CH stretch and the bends and so on. You can use this projection operator to generate all of those. So what do we mean by projection operator? Well, think of it just a regular projector like we have here in the class. It has to have a source of light, okay, that is then manipulated by the imaging element to create the image. So the source contains, essentially what you're after, the light, but then the imaging element changes it some way and produces the image. So we have those 3 things here. We have the source, which is either a vibration or an atomic orbital. So for a vibration, if you have water, there's a couple of different kinds of bonds. You just pick one bond. It doesn't matter which one. So you pick the OH stretch on the left. And so that's going to be your source. And you'll take that through the character table, and it will produce all of those arrow diagrams for the OH stretch. Or you could pick an atomic orbital. So you just pick the hydrogen 1s orbital. And we say, where will this 1s orbital go through the whole molecule as we go through each row of the character table? And what images will it produce? It won't produce the full molecular orbital, typically, unless it's just 2 hydrogen atoms like H2. But it will produce symmetry-adapted linear combinations of those hydrogen orbitals. So we then have the imaging element, which is the character table. So in this molecule, that's governed by the point group. So once again, if you get the point group wrong, then your results are going to be garbage. So it's really dependent upon the symmetry of the molecule. So if we take these these two sources and we run them through the A1 row on that character table, as we do a C2 on it or a flexion or something, those plus ones will govern either the direction of the arrows or the color of the 1s orbital. And so if we go through different rows, when we get to some minus ones, the arrows will change direction, or the colors of that red 1s orbital will change to green, and we'll get the molecular or the symmetry adapted linear combination of all of the symmetry connected elements. So if this hydrogen's connected to the other hydrogen by symmetry operations, then those will mix together. And that's what we mean by linear combinations. How do we have these linear combinations? What makes them linear? Well, they're not squared. They're not square rooted. They're just pluses and minuses. So we're just adding and subtracting those combinations of atomic orbitals. And this is what we get for the A1 row. So if we take this source and project it through the A1 row of the character table, which is our imaging element, we get these two images. And so that's where the symmetric stretch comes from. And so that by definition has to be A1, because that's the row that gave us that arrow diagram. So this is an unambiguous way to get the stretches or the atomic orbital combinations, and you automatically know their symmetry because you used that row to generate them. So let's practice. Today we're going to go through a couple of examples of this. So let's, and this would be what we call those normal modes of vibration. And so these arrow motions, and in Gaussian, then it would calculate the frequency of that vibration by moving those atoms just a slight amount, calculating the second derivative of that energy curve, and that would give you the vibrational frequency. And then these are the symmetry, the SALC-AO, symmetry adapted linear combinations of the atomic orbitals. Okay. So there's 6 words buried there. So let's see how these, we're just going to deal with the molecular orbitals today. If you want to know about the vibrational arrows, you can go to the Pchem YouTube channel, and it's the graduate course. We did the vibrations and the atomic orbitals. So if you want to see the arrows used on the imaging element, then you can look at the 5382 lecture, and you can see the same kind of lecture, but using also the vibrations. Okay, so let's look at homonuclear diatomics first. Pretty complicated character table. It's actually infinite in length, but I'm just showing you 6 of the columns here. And so this is the projection operator equation. It has 3 parts. This P for projection operator, and then up here this little superscript tells you what row you're on. And then the wave function is whatever wave function you're choosing, your atomic orbital. And it's going to take that atomic orbital and it's going to bounce it around to all the other atoms that are identical. So if it's a H atom, if you do a C2 or an inversion, it's going to go to all the other H atoms on that molecule. If they're what do we call it, chemically identical or chemically similar. And then it's a sum of these multiplied terms. So the green term are the characters. This Greek character chi is the character. And this OR, that O stands for operator. And I'm just going to call it the operator result, because it's the operator operating on the wave function. And so we're going to have the wave function go through these rows, and then we're going to have the results of those operations multiplied by the character. And then this sum is the add them all together, and you add them up. So that's the linear combinations. The linear part is the plus and minus characters, and then the combination is this sum. And when we add them all up, you're going to have plus and minus combinations of all of the different atomic orbitals. So let's just start with this. We pick one of the 2 hydrogen atoms and we put a 1s orbital on there. So we're going to start with this 1s orbital, and we're going to do an E operation on it. So if we do an E operation, here's my molecule, and I have this top orbital, and I'm just going to say this is this orange is unshaded. Okay. Now, the C infinity axis is the axis of the molecule. C infinity axis. And so if I do a C infinity rotation of that orbital, it's still unshaded because there's a +1 there. Okay, let's do a reflection. So if we reflect that molecule in one of these infinite vertical reflection planes, it stays put. Okay, and there's a +1 here, so it's unshaded. Let's do the inversion. So now if we invert that molecule, what's the operator result? The operator result moves it down to the other atom. So that puts it on this atom. And the +1 shows that it's unshaded. If we do an S infinity, so we rotate it 1/infinitieth of a turn and then reflect it down through the XY plane, it shows up on the other atom. And it's a +1, so it stays unshaded. And then lastly, we do a C2. The perpendicular C2s in the D infinity H are the like x-axis, y-axis. There happens to be an infinite number of those. We just pick one and rotate it. That moves it down to the other atom. And it has a +1 on it, so that's going to be unshaded. And so when we add up all of these results, we have 3 results where the 1s on atom A is unshaded, and 3 results where the 1s is moved to atom B and it's unshaded. And so this top row gives us this picture here. We have 1s on atom A plus 1s on atom B. It ends up being 3 plus 3, but the coefficient's really not important if they're all the same. If it's 3 plus 3, you just pull the 3 out front. That's going to end up being converted to a normalization factor of some sort. And so the real important part is it's 1SA and 1SB with the same sign. They both have a plus in front of them. Okay, so that's our top row, fully symmetric, linear combination of the atomic orbital of 1s. Okay, let's do one down here that gives us a different result. Okay, so down here, we're still going to have these same kind of pictures, okay, because the pictures come from these operations. These are the operation results. So our pictures for this row, I'm just going to draw them right here. We have the top orbital is still unshaded. Same here, this one is unshaded. And same here, this one is unshaded because I have +1, +1, +1 for those 3. But when I do the inversion, it goes to the other side of the molecule, and it's a -1 because it's shaded. That -1 tells me that it's now shaded. Doing the S infinity operation, it flips to the other side, and that -1 tells me that it's shaded. And then for the C2, it flips to the other side, and that -1 tells me that it's shaded. And so if I combine these 3, I have 3 unshaded ones on atom A and 3 shaded ones on atom B. Therefore, it gives me this picture, which would be the 1s on atom A minus the 1s on atom B. And they have different signs, which means they are different colors the way we draw these orbitals. And so that would be the A1U row. So I know also the symmetries of this. This is A1U and this is A1G. Now, what about one of these other rows that doesn't have? I mean, let's pick this A2. So let me just see. This is a +1. This is a +1. This is a -1, and so it kind of confuses things on this atom A. This one's going to produce a shaded one on top, and this one's going to produce a shaded one on bottom. And so the A, because we're missing some rows here and here, or some columns, I should say, what we would have, and we'll see this in other operations today, is that the A1s will both be shaded and unshaded. So you have a couple of A1s with +1s and a couple of A1s with -1s, and so you end up with 0 hydrogen 1s on atom A. You have let me say that again. Because some of the 1SAs have a +1 in front of them, and the 1SAs have -1 in front of them. When you add them together, they cancel each other out, and you get 0 1SAs. And then the same thing happens to the 1SBs. You have some positives and some negatives, and they equal each other, and they all cancel out, and you get 0 for that. And so when you get to the end, this row of the projection image element is dark. It is equal to 0. So you add up all of those atomic orbitals, and it ends up being a 0 result. And we'll see that today in water. We'll see that today in ammonia. So when we take the 1s on atom A and we project it through this character table, we only get 2 combinations of the atomic orbitals. Now that makes sense because you only have 2 atomic orbitals. So you should have only 2 combinations. And think about it logically. They can either be the same color or different color. That's all you can do. But this tells you which row they're on, unambiguously. So that's very nice. So here we have A1G and A1U. Remember, those colors indicate oscillation or expansion and contraction. One time they're expanding together and contracting together, and that's the A1G motion. The other is they're expanding and contracting at different times. They're out of phase with each other, and that's the A1U motion. It happens to be along the Z-axis, and so that A1U is also got Z symmetry. And like we said before, the much larger box for that molecular orbital drops its energy, and then the higher curvature of the other one increases its energy. So let's practice on water. Close this door. Now, if you'd like to follow along, I've deleted the math on your handouts, and so you can follow along with these calculations. So we still have the same kind of thing. We have the projection operator, and the little superscript is the different rows that you're on. We have the characters, which are here, and we have the operation on that wave function, which is really each column gives us a particular operation. So if we're going to do the A1 row first, we pick the 1s on atom A. So we're just going to pick that hydrogen 1s orbital on atom A, and we're going to do an E operation on it. So what do we do if we do an E operation on the 1s on atom A? Nothing really, because it's an E. So I'm just going to draw these up here just so we see. Let's go through the operations first. So let's just do these pieces right here. Okay, what if we did a C2? The C2 in this molecule rotates it around the Z-axis, and so that becomes a 1sb, right? So we're taking a C2 on that hydrogen, it moves over to B. If we do a reflection in the XZ plane, look here, this is the XZ plane. So that's the plane coming out of the board, so it hops over to atom B. So 1sb is the result of that. And then if we reflect it in the YZ plane, it stays put, so we have 1sa. So in all of these calculations, this is the order of our orbitals, okay? Because we operate on those are the results of those operations. And then the characters in front are all in the character table. And that's what gives us what row we're on. So let's do the A1 row. If we take, again, it's the sum of the character times this operation result. So it's +1 times the 1sa. See the 1sa here, that comes down here. And the +1 is this character right here. And then we do the next one. We have a +1, and this is multiplied against the 1sb. That's the result of that operation. And then the third column, we have a +1, because that's the character, times 1sb, because that's the operation result. And then lastly, we have a +1 times 1sa, because that's the operation result. And so you can see we have 2 1sas and 2 1sbs. The 2s can be pulled out front and normalized, and really what we end up with, the important stuff, is 1sa plus 1sb. So that's going to be our fully symmetric or totally symmetric combination of the hydrogen 1s orbitals. Now this is not yet a molecular orbital. This is the combination of the hydrogens. And if you think about those hydrogens, they're identical, and so their clouds are going to communicate with each other, right? Just like you have 2 guitar strings that are trying to play exactly the same frequency, they'll communicate with each other. They will reinforce each other. and these two hydrogens have 1s orbitals, and those orbitals can either be exactly the same frequency or exactly the opposite frequency. If they're somewhere in between, eventually, like a nanosecond, probably like a femtosecond later, they'll get in phase with each other. If you don't believe this, even in macroscopic objects, go on Google or YouTube and look at that one with the metronomes. They have all these metronomes sitting on a board, and they're all set to the same frequency, and they're all out of phase at the beginning, and a few minutes later they're all together because they have the same spring constant, and then the moving motion of the board that they're sitting on allows them to talk to each other. And these orbitals have the same spring constant, if you will, and they're all on a molecule which can allow them to communicate with each other. And so these linear combinations will appear very quickly when you build this molecule. Now, this is just the hydrogens. What could they oscillate with? Well, they're going to also oscillate with the 2s on the oxygen and the 2p's on the oxygen. And that's what forms the molecular orbitals. But we've got to build this up a piece at a time. So we're going to build it up with the identical elements first. So an individual hydrogen atom it's because there's an identical hydrogen atom on the other side of the molecule, it doesn't act by itself. It's going to immediately communicate with that other hydrogen because they're identical. Okay, let's do the second row. So the order of those orbitals does not change. We still have essentially A, B, B, A in our orbitals. Do you understand what I mean by 1s A, 1s B, and so on? So A, B, B, A is our order of those operations. And so our character is a +1 here and a +1 there for the 1sB. You see, I'm just pulling down the second row, characters. And then I have a -1 times the 1sB and a -1 times the 1sa. And so this is what I was talking about earlier with the hydrogen combinations that we did. The 1SAs have a plus and minus sign, so they cancel out, and the 1SBs have a plus and minus sign, so they cancel out. So there is no A2 combination of these hydrogen orbitals. Okay. If I'm going too fast for you, just have to check the video. Okay. Again, it's enrichment, so I enjoy to see you all writing this down. So then let's do the B1 row. Okay, so again, the same order, A, B, B, A. The +1 from the B1 row, then the -1 for the B, and then we have a +1 on the B and a -1 on the A. So once again, the A's have 2 of them that are plus minus, and the B's have 2 of them that are plus minus, and so they all cancel out. So there's no combination that has a B1 symmetry. It's really useful information. I know exactly what my combinations are going to be. We've got 2 atoms, and with 2 atomic orbitals, we better have 2 combinations that match. And so we've only got 1 so far. So this last one ought to be valid. If it's not, then we've made a mistake somewhere. Okay. So the number and types of orbitals is conserved. Okay. Okay. So then let's do the B2 row. So we have that first character 1, +1 times 1sa, a -1 times 1sb, another -1 times 1sb, and a +1 times 1sa. And so now both the b's are minus, both the a's are plus. We can pull the 2's out front and set that in a normalization constant, but the real information is in the change in sign. So we have a 1sa minus a 1sb. And that's the other combination of these 2. You knew that they were going to be both in phase or one, out of phase. But which row was it on? It's on this row. It also tells you that it has the same as Y symmetry. It's on the Y row. And so that's B2. That's why I don't teach this projection operator at first. It's really quite involved. It takes a long time. Whereas if you just drew this picture, like we talked about before, with that assigning Millikan symmetries, if I stand right here and I look to left and right, I see a change in sign along the y-axis, and I say, yeah, okay, it must have Y symmetry. So I find Y symmetry, and it's B2. But that's sort of going backwards. This is the forwards way to get to that same picture. Like, where did that picture even come from? It came from the projection operator. So from two atomic orbitals, they combine in water. The linear combinations of atomic orbitals are here, the 1sa plus 1sb and 1sa minus 1sb. These are two nuclei that are indistinguishable, and so those are the only two that are going to combine in this area. And then we go to the full molecular orbital and combine them with the oxygen valence orbitals. Two AOs will give two MOs, and vice versa. And then these three, like we're going to do one with ammonia. 3 1s atomic orbitals in ammonia, because those 3 hydrogens are identical, will combine to produce 3 molecular orbitals or 3 symmetry adapted linear combinations. There's the symmetric combination, which naturally you would expect to be 1sa plus 1sb plus 1sc, and that's going to be top row most likely. We'll see that. But there's also the asymmetric combinations. Now this one's not so clear. We'll look at the projection operator, but I'm kind of giving you the answers here for ammonia. We don't have the symmetries listed with these, and we'll get them when we do the projection operator. Okay, so let's go back to water. Here's the 2 symmetry adapted linear combinations. We could put these in order of energy. The one with no nodes is in the lower energy. The one with 1 node is a higher energy. And so this is how you would have that. These would combine with the oxygen valence orbitals. The 2s orbital is going to have the symmetry of A1 because it has, again, all of these squared elements. It's x squared, y squared, and z squared. And then the 2p, x, y, and z, they tell you what the symmetry are, x, y, and z. And so the x is going to be B1 because we have x on that row. The y is going to be B2, and the z is going to be A1. And so if we were to make a molecular orbital diagram for water, those orbitals that have the same symmetry are going to mix. So the 2s orbital is not going to mix with the B2 combination of hydrogens, but it is going to mix with the A1 combination. And so if we bring that 2s orbital in phase with this A1, then it's just going to smear that electron density over the whole molecule, no nodes. That's the lowest energy one. Okay. If it's out of phase, meaning let's say the hydrogens are green while the 2s is red, notice you're going to have something like this. With a node here. Okay. Notice that's very similar to this 2pz. It has a shaded on bottom and an unshaded on top, if you want to call red unshaded, and has 1 node. And so that one, this 2s combination and the 2pz combination are going to be very similar. Just the difference is the location of this node. Is it on the oxygen atom or slightly below the oxygen atom? And so essentially that's going to be the same molecular orbital. So we have 3 A1s. And so we're going to end up with 3 molecular orbitals. So we've got to come up with 3 pictures here that are the combinations of these 3 orbitals. And so the next one is this one. So the 2s and the 2pz are actually acting similarly with these hydrogens, again in the A1. And then the antibonding combination, or the highest energy one, looks very strange up here. This is because Gaussian's letting those electrons have as much freedom as possible. But what this one would be, if you wanted to draw it here, would be the p orbital on the oxygen, and here's the hydrogens. So you have the 1s's on the hydrogens and the pz on the oxygens, and this is shaded on the bottom. And so the hydrogens are unshaded, which means they're red. The top of that oxygen is unshaded, which means it's red. And then this part is shaded. Now Gaussian has let this thing go all the way around those hydrogens and still stay shaded, okay? But that's where that picture came from. This is something I would expect you to be able to draw, though. You just take the PZ on the oxygen, so the oxygen PZ, and then the we might say minus the 1SA minus the 1SB. so that oxygen Pz is out of phase with the 1sa and the 1sp. I don't like that O in front. It looks like a 0, so I'm going to erase that. I'm just going to put a 2p, 2pz. Okay. So those are the A1 combinations. They don't have anything to do with the B2 on the hydrogens. So let's combine the B2. Which one of these is going to interact with the B2? Well, the 2py, because it's also B2. And it's going to be in phase like this or out of phase like that. Now, again, that's a really kind of hard to understand picture, but it's not too bad if you draw just the water molecule. You put the py orbital on the oxygen and shade the left side, and then the hydrogens are going to be out of phase with that. So this guy's going to be shaded on the right. And you see all those nodes. You've got nodes here, you've got nodes down the middle, you've got nodes there, you've got lots of nodes. So it's going to be high in energy. Whereas down here, the shaded and the unshaded match the hydrogen, they're in phase, and so you just drop down in energy because the electron gets to spread out. Okay. And then we're left with the non-bonding orbital, this px. It has nothing to interact with because it's B1 and it's by itself. So it has no linear combinations to interact with, and so it comes straight across. So that's where we get this molecular orbital diagram for water, is these symmetry adapted linear combinations that we get from the projection operator. And then each one of those is an energy level. We come in with 6 valence electrons with the oxygen, plus 2 from the hydrogen, so we have 8 valence electrons, so we just populate that from low to high. And this would be the highest occupied molecular orbital. And this is the LUMO, the lowest unoccupied molecular orbital. And that would be the longest wavelength transition right here, taking that electron up from the HOMO to the LUMO. And if it's going to show up in the visible spectrum, that's most likely the peak that you would see, because that's the shortest distance, which means it's the longest wavelength. And that is if it's allowed. And so you could look in this and go back to the character table and see if a B1 to a B2 is allowed by X, Y, or Z polarized light. And that's definitely something that you should know how to do. We've done that quite a bit. Let's work with a molecule that's more three-dimensional, okay? And something that has an E row. So something that has a two-dimensional Millikan notation. Now, this is a little different character table. Look at this character table. It's had to be expanded. You know, if you look in your character table, it really only has 3 columns in the ones that I've been giving you. It has an E, a C3, and a sigma V. But for the projection operator, we need to split out these 2 C3s. There's a C3, which is like a clockwise rotation, and then the C3 minus 1, which is a counterclockwise rotation. Because there's 2 of them. You can go to the right or to the left and move that hydrogen around. Same with the sigma V's. There's 3 reflection planes. Every NH bond is a reflection plane. It reflects the other 2 hydrogens into each other. And so for our projection operator, we need all 6 of those symmetry results. So we have to expand the table a little bit. So let's, again, we have the different rows for our projection, our characters, and then the results of our operations. And I've labeled the atoms A, B, and C like this, A, B, and C. So let's work through a few of these here. So let's do the A1 row. So this superscript tells us we're on the row A1. I'm going to write my letters up here. So if I do an E on 1SA, look here, this is atom A, I do an E. E doesn't ever change anything, so that's still A. If I do a C3, we're going to call this a rotation back here. So the C3 brings it over to atom C. And so this first C3 is giving us a C. Going a C3 minus 1 moves it the other direction. And so that gives us a B. So it goes ACB. Now the reflection planes. The first one is going to be the one that contains this bond. And so that'll be sigma V. And so it doesn't do anything. That orbital is just reflected into itself. And so that's going to be an A. The prime I'm going to call this one single prime, this reflection plane, which reflects the A into the C. So this one's going to be C. And then the double prime will be the one in the back, which reflects A into B. So that's the order of my 1s orbitals. That's where they went with all these operations. ACB, ACB. And you can see that down here, A, C, B, A, C, B. Now we can put our characters in there. So I have a +1 in front of this 1SA, a +1 on the C, a +1 on the B, and then we do it again, +1 on A, +1 on C, +1 on B. So I have 3 of each, no, 2 of each. And so I pull those 2's out front. That will go into a normalization constant, and the information I care about is just the plus and minus signs. So this is the fully symmetric combination. No surprise, it's top row, and so it's going to be A1. No G's are used because there's no inversion center on this molecule. Okay. Now let's do A2 row. Same order, ACB, ACB, and now we have +1, +1, +1 for ACB, so we see that here, and then we have -1, -1, -1, which cancels them all out. And so my A's are canceled, B's are canceled, C's are canceled. And so there is no combination of the hydrogen 1s orbitals that has A2 symmetry. Okay, now for the fun one. Okay, this doubly degenerate row down at the bottom. Same order, ACB, ACB. And then we have, because this is doubly degenerate, we have a 2 as our character. So this is the first time E actually is different. Okay, E has something interesting here. So that 2 goes right there. So we have 2 1SA, and then the C is a -1, okay, and so is the B. And then we have zeros on all 3 of these. And so those 3 are canceled out. And so we end up with this. Now we can't get rid of the 2 because it's important. It can't be pulled out and stuffed into a normalization constant. And so we keep it. So it's a 2 times 1SA minus 1SC minus 1SB. So what does that mean? Well, it kind of means that 1SA is twice as big, and 1SB and 1SC are shaded, the minus signs. Let's make the minus signs shaded. And so that's what this orbital looks like. It has a node right down the middle. Since there's 3 orbitals, and there's only one way to be out of phase, we've got to split them up, right? A goes here and B and C go over here, but it's not quite even, is it? And so we're going to have twice the effect on atom A. And so it kind of balances out so that node is right in the middle. And so A is really changing a lot in this situation. That's what the 2 tells us. And the B and C is just changing a normal amount. Okay. Now, the other combination is, if we've used A sort of having twice the effect, if we put the node along the A axis, that A bond, 1SA bond to the nitrogen, then it can't participate at all because it's a 1s orbital. That node splits that 1s orbital. And so it's just not used in the second combination. The second degenerate set is 1SB minus 1SC. We don't get that from the projection operator, though. We can't get that from this row. We just have to know if I've used A twice, then I use it 0 times here. I've used B and C once, here I use them once again. B and C have the same sign here, they have different sign there. So those are the 3 principles that you use to create the second set, second of the set. So these are the pictures of those symmetry adapted linear combinations. They're actually pictures of the molecular orbitals. We've combined them with the nitrogen orbitals, but you can see that effect. So this is the A1 wave function, which has that 1SA plus 1SC plus 1SB, and then that 2 1SA and the minus 1SC minus 1SB just indicates they're different colors. And you can see that 1SA is twice as large, and you see that node goes this way. Now in these this is the way it works with all threefold and higher symmetries, that you can have this sort of node balanced in one plane, and the other is going to be 90 degrees to it. So that's another way to know. You take that node and rotate it 90 degrees, and what do you get? That node's on the hydrogen A right now, and so it destroys that 1s orbital, and you only have combinations of C and B that are possible. And so then that have that 1sB minus 1sC, giving you the other degenerate set, and the node is 90 degrees. You see that? And in our Cartesian symmetry, both of these are the E. Let's see. I'm going to go ahead and draw the Cartesian axis here. So the z-axis is coming out of the plane of the paper. Okay. And this is x, and this is y. And so this one has y symmetry because it's oscillating in the y direction. This one has x symmetry because it's oscillating in the x direction. And you can, if you put one of these axes along one of the bonds, then it's cleanest. It's the cleanest way to draw it. And so that y-axis is along this bond, and so this is going to be the y, and this is going to be the x. So that's how we get these three combinations of the three orbitals on the hydrogens. And then they'll mix with the nitrogen 2s and the nitrogen 2p orbitals. And we're going to do that, let's see, what is today? Yeah, today's Wednesday. So we're going to do that on Monday. So on Monday, we'll do the phosphorus pH3 molecular orbital diagram. On Friday, we'll do on blank sheet of paper from start to finish the chlorine phase diagram. And so you'll notice the notes are just a single sheet of paper. Okay, we're just it's gonna be all board work, but it's gonna be on the computer, so it's a video. But we'll just work by hand from scratch, doing the MO diagram for a homonuclear diatomic. And we'll talk about a heteronuclear diatomic, and then on Monday we'll expand that to a threefold system like this. And that's as complicated as it's gonna get. Okay, it's definitely doable. So these symmetries are the molecular orbitals. You should be able to take these pictures and assign their symmetries, though. So if you got all three of these pictures, you should be able to go to the character table and say, that's an E, that's an A1, or, if there was an A2, you should be able to see it, okay? So you look at this orbital here, you draw the Cartesian system, you say this is changing color on the left and right, the x-axis. You could think of it as expanding here and contracting there. Sometime later, it expands here and contracts here. You see, if it's expanding and contracting like that, it's moving in the positive and negative x direction. It has x symmetry. And so you just simply go find x in the character table, and it's E. Same with this. If it's expanding and contracting along the y-axis, it has y symmetry. So you find that, and it's E. Here we have the same motion in x, y, and z in all directions. And so it's x squared, y squared, z squared, just like a sphere. Only it's really not a sphere, but it's like a sphere in that it's the same in all directions. Okay, so that's top row. And so then you can be able to do that. Now level up. If you want to level up and understand how to communicate with me, you should be able to look at these pictures and come up with the shorthand, or if given the shorthand, draw the pictures. So you practice on that just for fun. Okay. And I may even do a multiple choice to say, okay, you've got this orbital picture, which is it, A, B, or C? Right. And you could look at that and you could say, well, they're all in phase. So I have the 1SA is a plus. I could put a plus in front of that, a plus 1SB, a plus 1SC. They're all the same, so it's probably this one. So I would pick C. Okay. And if I picked this one, like if I said, all right, which one is this? I'm looking at that. I'm saying, look, A is kind of twice as big as B and C. If I'm going to label this A, B, and C. And so that's probably this one. Okay. If I come over here and I'm looking at this one, it looks like A is not even used. And so that's a real big indicator. I come over here, there's not even a 1SA over here. Okay. even though these aren't labeled, I'm looking at this and I'm saying, look, I'm only using 2 orbitals and they're out of phase with each other. That's got to be this one. Okay. All right. And so that's all I've got. 850, can you believe it?